Hello, everyone. This is Whit from Brainstem Tutoring, and today I want to talk about the quantum numbers. We get into the quantum numbers when we're talking about the structure of an atom. The way I like to think of the quantum numbers is sort of like the mailing address of every single electron. You know how, at least in America, you have the state, city, street, and street number where somebody lives, right? Well, every electron has a home and it has this N, L, M sub L, and M sub S number. So each electron has four of them, but they mean some stuff too. We need to talk about that. And there's this weird number rule for each of them. What are the acceptable numbers? So the first number is N, or the principal quantum number. Principal quantum number. It's often called the shell or level. It determines the energy of the electron. Every electron has some amount of energy. The bigger the N, the more energy is. Also, the further it usually is from the nucleus. Here's the rule. The principal quantum number can be any whole number starting at 1, going up forever. We usually don't talk about it going up forever. We usually max out around 7, but start at 1, goes up to positive numbers. No decimals, no 0, no negative numbers. That number is fairly straightforward. Okay, so if you live in the state of North Carolina, that dictates some of the cities that you can live in, right? So the possible range of L numbers is borrowed from math, the interval notation. So it's including 0 up to n minus 1. We'll talk about that more in 2 seconds. But quantum number L also has to deal with some energy. So the higher the L, the higher the energy. But most importantly, it deals with the shape of the electron. Not like the actual shape of the electron, but more so the shape of where it's hanging out in. Like, is it hanging out in a round yard or a rectangular yard or something like that? That's what I mean by the shape. So, some examples. If N had equaled, let's say, 3, L could equal 0, 1, or 2. If N had equaled 4, L could equal 0, 1, 2, or 3. That's what this math interval notation means. I'm not saying that it equals every single one of them. For every state that you live in, there's multiple cities, right? But nobody has a home address with more than one city. So we'll talk about it more later, but one of these numbers, each electron has one L. But there's many possibilities. To get more into L, what I also want my Clemson students and all chemistry students to know is that the L's mean something. When L equals 0, we're talking about the S shape. That means electrons are hanging around in spheres. There's some electrons somewhere in that three-dimensional sphere. When L equals 1, we're talking about the P shape. That looks like a dumbbell. Bow tie, pasta, whatever. I call it a dumbbell. Now, when L equals 2, we're talking about the D shape, and there's 2 possibilities. 4-leaf clover, which looks like 2 dumbbells, or a dumbbell with a ring around it. And there's some electrons hiding out somewhere in those shapes. When L equals 3, we're talking about the F shape. Those shapes get pretty complex to draw. I'm not even going to try to draw them because they're usually not asked about in Gen Chem college exams. But you can describe it as like 2 M&Ms and 4 kidney beans, stuff like that. So I want you to know those shapes very well. So therefore, something that usually trips up students, if we have this shape, you immediately know, L has to equal 1. And then you think backwards to what could have N equaled. There's multiple answers, right? N could have equaled 2, 3, 4, 5, and so on. N could not have equaled 1, and n could not have equaled 0, because that's impossible in the first place. So that's a typical question. How to go backwards once you know L to what are the possible n's. Okay, so that's that. Now M sub L. This one doesn't tell you about the energy of the electron. It just tells you about the orientation of the orbital, of where the electron's hanging out. The possible, so number, some background, this is called the magnetic quantum number. It gives us the orientation of the orbital. And importantly, that tells us how many orbitals there are. For example, number rule. M sub L, the possible range, is from negative L to positive L. Example, if L equaled 1, M sub L could equal negative 1, 0, or positive 1. Now, those numbers don't mean a lot. What's more interesting and important is the fact that there's 3 of them. That tells us there's 3 different ways that the P block or the P shape can be oriented, which makes sense. X-axis, Y-axis, and Z-axis in 3 dimensions. Don't worry too much about that. Just know that there's 3 options. It tells us how many orbitals there are. So another example, if we're talking about L equals 2, aka the D block, M sub L could equal negative 2, negative 1, 0, 1, or 2. Aka there's 5 orbitals in the D block. Cool. Last number is called the spin number. Finally, we're getting down to like the nitty-gritty of the electron. The electron is somewhere in the dumbbell shape, in the x-axis orientation or whatever like that. Now, there's 2 ways an electron can spin, in the positive direction or the negative direction. That is why there's only 2 options for M sub S. Positive 1/2 or negative 1/2. You have to do a little bit of physics to understand which way is the positive direction, which way is the negative direction. It's something called the right-hand rule. You don't need to know that for Gen Chem, but if an electron is spinning, let's say, from the bird's eye view in the clockwise direction, that would have the negative orientation. And then if it was going counterclockwise from a bird's eye view, I would say it's going in the positive direction. That does not matter. You don't have to worry about it. I just want you to know that there's 2 options. Either the electron spin in the positive direction or the negative direction. Wonderful. I want students to be able to answer questions like, what does the shape physically mean? And also, what is a legal set of quantum numbers? I want you to know, for example, that if I had 3, 2, 3, negative 1/2, that would be an illegal set of quantum numbers because M sub L does not fall into the proper range. Things like that. Those are typical questions. I hope that helps shed some light on quantum numbers and the rules that you need to know for a test. If you have any questions, reach out to me, and good luck studying.